So here we are. We only have two kind of new lesson lectures left. We did 12 last term, and we'll have kind of 9 wrapped up by the end of this. And then the last 3 lectures of this term are kind of low-key. One is examples. Again, start sending me messages if there are particular example problems you'd like to work on. I'll probably go through a steel column, steel beam, wood column, wood beam, concrete column, concrete beam, and that might be just enough for the entire lecture, just for us to kind of go through. And then we have our beam testing, and then the last lecture is just something you get to listen to. Pop some popcorn, sit and relax, and enjoy yourself. So today, and actually next week, the math isn't hard. It's relatively low-key math. I'm going to show you some equations in a few minutes, and you're going to say, you lied to us, Hilchi. You said this was going to be easy math. It's going to look complex for a very brief amount of time, and then we're going to go through an example, and you're going to be like, oh, that was way easier than it seemed like when we looked at it as we derived this process. So what we want to start talking about is our next material, and our next material is concrete. It's one of the biggest ones we use in the industry: steel, wood, concrete. Those are the 3 heavy hitters in the construction industry. Concrete has serious flaws, but if used correctly, it can be a wonderful construction material. Should it be used as much as it is? I don't think it should be. It has a lot of detrimental environmental problems. But as a structural engineer, it is a beautiful, beautiful material. One of the things that is awesome about it is that it is composite. We've seen some things that are composite in our past lectures or talked about. Glulam is composite, concrete on metal deck is composite, but we don't really know what that means. So this lecture, as kind of the introduction to concrete, is to talk about composite, because our reinforced concrete is concrete with steel in it. And in fact, even the concrete itself is a composite material because it is sand and rocks and liquid and Portland cement all mixed together, working as one thing. And unlike steel, where it's melted down and you would need a microscope to see the different things that made this one element, concrete, you can bang it with a hammer and see the rocks, you can see the sand in that system. So how do those things all work together, and how can you possibly analyze it? So we're going to talk about composite action. And there's a few ways to start talking about composite action. Ultimately, we want to know, what does it take for 2 different objects or materials to work as one thing? It could be 2 objects of the same material, it could be 2 objects of different material. What does it take to make them work as one? So before we talk about that, we need to know how materials can share loads. If we have 2 different materials, how can we even share loads between them? Because they've got different strengths and they've got different stiffnesses. So how can those things work together, even if they're not composite? So composite means we force them to act as one object. How do we even make it work if they're literally 2 separate objects sharing a load? So we're going to start with load sharing. I'm going to introduce you to a concept called transform sections, which is really just building on an easier way, or sometimes an easy way to talk about 2 separate materials. And then we're going to really look at composite action. And then I'll just show you some images of some materials we build with, or things we build with that are composite materials. So the first thing I want to talk about is load sharing. So what we have is the definition: when 2 elements or materials are arranged so that they mutually support the load, they are said to be load sharing. The proportion of the load that each resists is proportional to the stiffness of the material. Load will follow the path of greatest resistance, or the stiffest element. So that old adage, the path of least resistance, is complete and utter crap. load is going to be attracted to the most resistance. So the stiffer something is, the more load it is going to take. Now, obviously, depending on how much of it you have, is at play there. That's assuming you understand that if you have two materials that are the same and this one's bigger than this one, more load is going to go over here. We're taking that as kind of a thing we would understand. So visually you can look at something, and if they're the same material and one part has a bigger area than the other, you know intuitively that more of the load is going to go to that side. So I'm going to show you some examples in just a minute. What might not be as obvious is that stiffness also attracts load. So let's think about this for a second. Multiple elements supporting the same load share it based on stiffness. Load likes the path of the most resistance. I've already said that. Now, if you take a steel rod and wrap it in Play-Doh, which part of that is going to take more load? Now, we're not saying all of it's going to the steel, because we're saying your hand or whatever is sitting on that combination of things, the load is being spread out evenly over that. Which part do you think is going to take more of the load? The steel or the Play-Doh? And I think intuitively you understand that the steel rod is going to take most of the load because it's way stiffer. That's one where intuitively you would understand that. It doesn't matter that we have a ton more Play-Doh than we do steel. You know how not stiff Play-Doh is. So intuitively you get that most of the load's going to the steel rod. It becomes a little more tricky when you have something that's slightly stiffer. So if we have a steel rod wrapped in wood, for example, it's not exactly obvious. We know that the steel is way stiffer than wood. It's got 200,000 MPa for its E versus, now we saw wood changed around somewhere between 6,000 to 12,000 MPa, but way less stiff. But look at the amount of area of the wood here. So it's not completely obvious to me which one is going to take more load. I'd have some predictions, I think maybe the steel might take more of it, but they haven't told us what these areas are. But looking at it visually, I'm going to guess more is going to go to the steel, but it might be somewhere around 50%. The point is, it's not obvious when we're talking about stiff things together. The Play-Doh is obvious, it's not that stiff. But the wood and the steel together, it's not clear to me. But we do know area seems to have an impact on it, and stiffness seems to have an impact on it. So we need some way to talk about those things as a ratio of each other, maybe. So clearly, the area of the steel and the stiffness of the steel is important, and the area of the wood and the stiffness of the wood is important. And probably the ratio of those two things together is going to be very important. And that's exactly what we're going to calculate now. It's going to look confusing, mostly because we take some things, substitute it into each other, and then pull it back out and substitute it in again. But just remember, what we're really talking about is the ratio of area and stiffness of steel to the total, and the ratio of area and stiffness of the wood to the total. That's what we're about to derive here. So load sharing. The example we're going to talk about is a concrete and steel column sharing load. Now, to share load, they have to be squashing together. If one of them squashes more than the other, only one is left carrying the load. So for example, if I had that Play-Doh and steel, if I squashed the Play-Doh down but left the steel's then obviously carrying all the load. We're talking about load sharing, which means they must be moving together. They have to be sharing the load. So if they're squashing together, we know we're talking about strain. Remember, strain is a representation of deformation, or change in length divided by the original length. So that's the squashing. You guys remember our basic formulas: stress equaled force divided by area. We can rewrite that as force equals stress times area. We know strain equals the change in length divided by the original length. And stiffness, or modulus of elasticity, equals our stress divided by our strain. We can rewrite it as stress equals modulus of elasticity times strain, should we choose to. So this is just rewriting those two formulas. We can start to substitute some things into here. We've done this a bunch of times, depending on what we needed. Well, we're going to do the same thing here. Force equals stress times area, and stress can be modulus of elasticity times strain. So let's take this and plug this in here. Let's get my pen, maybe I can get my pen going here. So let's plug that in there, and we get force equals modulus of elasticity times area times strain, where E and A are for each material, or can be for each material. E has to have the same strain. Remember, strain is how much it moves relative to the original length. Well, if they're squashing together, the strain has to be the same. So E is going to be the same for both the steel and the concrete. So for each material, the force in the steel is going to be the stiffness of the steel times the area of the steel times the strain. And the strain is the same for both, or that amount that it deforms. The force in the concrete is going to be the stiffness of the concrete times the area of the concrete. That's that ratio I was talking about, times the strain. And the strain is the same for both of them. But we want to talk about this as the total load. Well, the force in the steel plus the force in the concrete should be the total, right? Which means the total force is our EA of steel and our EA of concrete, both times strain. Well, strain is the same for both here. These are the same strains. Let's just bring it outside of the parentheses here. So we have the total force is the total strain times EA of steel plus EA of concrete, or the sum of all the EAs. So the total force is the total strain times the sum of the EAs. We know that the force in the steel was the EA of steel times the strain, and the force in the concrete was the EA of concrete times the total strain. Well, the sum of EA is the axial stiffness of the combined system, or the total system. We can rearrange this if we want, and look at strain, because remember, the strain is going to be the same for both of them. We have the total force is divided by the sum of the EAs, or the total of all of our EAs. Well, the total force, we can rearrange this here, and we can plug this back into our Fs is the EA of our steel times our strain. Well, if our strain is our total force divided by the total EA, so we're taking this and plugging it in here, and we're plugging it in here. The force in the steel is the total force times the EA of steel divided by the total EA. The force in the concrete is the total force times the EA of the concrete divided by the total EA. If you look, this is just a ratio, or the percentage of load that's going to go to concrete and the percentage of the load that's going to go to steel, or the combined stiffness of the steel divided by the total stiffness, or the total stiffness of the concrete divided by the total stiffness. Because some of it has to do with the material, and some of it has to do with the amount of material we have. So this lets us know how much of the force is going to go to each material. We can talk about it as a ratio, should we want to. So we're being a bit of a pain here, but this is literally what I've already shown you. You didn't there's nothing new here. So this is, it looks like I tried to clarify these slides a little bit. So here it is right here. Here it is written out nicely for us. This is what we just looked at on the other slide. The force in the steel is the total force times the ratio of steel stiffness, which is the EA of steel divided by the total EA. And the force in the concrete is the total force times the stiffness ratio for concrete, or EA of concrete divided by the total stiffness. I know, that looked very, very, very confusing. I think the best way to illustrate this is to do an example. So for our load sharing example, they've told us we have a steel 152, HSS 152 by 152 by 9.5 filled with concrete. What load in kilonewtons does the steel carry, and what load does the concrete carry if the stiffness of the concrete is 30,000 MPa? Well, they didn't give us a total load, so it looks like we need to know what percentage the steel will carry and what percentage the concrete will carry. Let's just start with an exercise here. Right in the corner, what do you think is going to carry more load, the steel or the concrete? It's not obvious to me. We know that there is way more concrete than there is steel. So the area of the concrete is greater than the area of the steel. But our E for steel, we know now, is 200,000 MPa. And the E of the concrete here is only 30,000 MPa. And we know that it is a combination of stiffness and area that attracts the most load. So the total stiffness of the object, which is based on the material stiffness and the amount of that material that we have. So it's not obvious to me. I'm going to guess somewhere around 50-50. But I don't think that's perfectly right, but it's not almost all steel or almost all concrete would be my personal guess. So I'd be happy, plus minus 20% there, but somewhere around 50-50 with a broad margin. So I'm going to write for myself, I'm going to draw it out here just because I can. Drawing my steel HSS, and this is an HSS 152 by 152 by 9.5, and this is concrete with an E of 30,000 MPa. I'm going to say around 50%. 50%. I know that's not right, but it seems to me somewhere in that range might possibly be right. So the first thing we should do is kind of figure out what area and what stiffness we have for each material. So let's start with the steel. The E of steel, we know, is 200,000 MPa. We know that. We've been talking about it a lot. We know it's been tested again and again and again. The area of the steel, we could manually calculate that, but we know that they have a steel property table, so we can go look up the exact area of this HSS. So if I go to that steel sections PDF, it'll show me that I have an HSS 152 by 152 by 9.5 with an area of 5,210 millimeters squared. And that came from the PDF of steel sections. Concrete. Well, they gave us the E of concrete as 30,000 MPa. And we need to figure out the area of the concrete. We know that this dimension is 152, and we know that this dimension is 152. Yeah, the edges are rounded off, but we've got a little bit of steel there. I am not going to worry about the rounded edges, because overall for the area of the concrete, that is a very small difference. I want to know what this dimension is from inside to inside here. Or, essentially, 152 minus 9.5 times 2. So this dimension is 152 minus 9.5 minus 9.5 times 152 minus 9.5 times 2. So this dimension times this dimension is going to give me my area. 152 minus 9.5 times 2. 133 times 133 equals 17,689 millimeters squared. So I have my EA of steel and my E and A of concrete. We know that actually calculating the EA, the combined values of those, is important. So EA of steel is going to be 200,000 times 5,210. And I want to write these here, one right above each other, just so that we can kind of see the difference. We can see that our steel is much stiffer than our concrete, but we also have much less area of steel than we do concrete. Let's see what those values are. So 200,000 times 5,210 for the steel. And we have 1.042 times 10 to the 9, and the EA is going to be in newtons. Oddly enough, we had newtons per millimeter squared, and this was millimeters squared. So we have newtons, and we have our 30,000 times 17,689, or 0.531 times 10 to the 9 newtons. So it looks like the combined stiffness of the steel is quite a bit more than the combined stiffness of the concrete. Anyone starting to make a revised guess about which one you think is going to take more load now? Now we know that the total load for each material is dependent on the total stiffness of the system. So we also want the sum of the EA, or the total EA of the system, which is going to be EAS sorry guys, just an Amber Alert here. I want to read it. Bayfield, Ontario. Where's Bayfield?
Cottage Country.
Black Mercedes SUV. Unlikely we'd see it here, but eyes peeled. So the EA of steel plus the EA of concrete, or 1.42 times 10 to the 9 plus 0.531 times 10 to the 9. So the total combined stiffness of this system is 1.573 times 10 to the 9 newtons. The force in the steel is the total force times the EA of steel divided by the total EA. Or the force in the steel is the total force times EA of steel, which is 1.042 times 10 to the 9, divided by the total stiffness of the system, 1.573 times 10 to the 9. Or the ratio of that total stiffness that is due to the steel. So 1.042 divided by 1.573 equals 0.662 F. Or the steel is going to take 66.2% of the force. Well, that was pretty close. I guessed 50. It's a bit higher in the steel. I knew I was going to be happy with like plus minus 20% here or something like that. So it wasn't obvious which one was going to be more, but it looked somewhere around sharing them somewhat evenly. So we now have the percentage that's going to the steel. We know that 100% is the total. We could take 100 and subtract the percent going to the steel because the rest is going to the concrete. Or we can calculate it. The total force times the EA of the concrete contributing to the total system. Or force times 0.531 times 10 to the 9 divided by 1.573 times 10 to the 9 equals 0.338 times the total force, or 33.8% of the total force is going to go to the concrete. So that's pretty handy. What if someone gave us a total force of, let's say, of 3,000 kilonewtons? The steel HSS is going, so let's say this was PF. They gave us a PF. So the steel HSS is going to have a PF of 0.662 times 3,000, or 0.662 times 3,000. We need a PR of that HSS greater than 1,986 kilonewtons. Because remember, we want this to be less than PR. And our concrete PF is going to be 0.338 times 3,000. Or 1,014 kilonewtons, and we're going to need that to be less than the PR of the concrete. So for this system to work, we need to be able to check that the steel works and the concrete works. But that means we need to know what load goes on the steel and what load goes on the concrete. Once we know that, we can assess the capacity of the steel and the capacity of the concrete. Steel, we know we have a very complicated equation, but it seems like buckling would be a little bit different because it's filled with concrete. We're going to ignore that part for right now. But now all we need to do is calculate PR and PR for the steel and PR for the concrete, and we know if this column works. That is worked out here for you as well. So that was handy to relate the stiffnesses of the materials relative to each other. Sometimes it's going to be a little bit handy to actually just pretend we have one big object, or one object of all the same material. So even though we have steel and concrete, sometimes it's handy to say, we want to talk about it as if it was all concrete, or let's make our steel, what's the equivalent concrete that would equal that steel area? So that steel has an area and a stiffness. What would be the same equivalent stiffness and area if it was concrete? And this is what we call transforming the section. And this is really handy when we do concrete beam design. So I'm going to show you what that looks like, and we'll do two examples. Knowing that it is just a kind of a back pocket trick engineers use, rather than kind of keeping this concept of steel and concrete separate, we'll actually pretend it's all one material. It all still comes back to this ratio of stiffnesses though. So remember, we have our strain equals our total force divided by the sum of all the EAs, or the entirety of the stiffness of the system. So for any object of any material, or a combination of them, it'll act the same as long as the sum of EAs is the same. What we care about is that entire system has the same total stiffness, or combination of EA. It doesn't matter if we changed E, as long as if we lowered E, we'd have to increase A. If we increased E, we'd have to lower A. What we want to know is that this entire stiffness stays the same. It should be the same. So how would we do that? Well, if we had a material with a different stiffness, we could figure out what corresponding area we might need to make that an equivalent system. So if we have an EA of 1.57 times 10 to the 9 MPa, it could either be, we just know that that's a total. E could be 1.57 times 10 to the 9 MPa, and A could be 1 millimeter squared. We don't know, we just know the total here. Or E could be 1 MPa, and area could be 1.571 times 10 to the 9 MPa. Looks like slide 10 has some subscript and superscript problems. So what we care about is keeping this total the same. And we know that for a system, and we just did it, we can figure out what the total EA is. We figure out what the combined EA of the steel is. We figure out what the combined EA of the concrete is, and then we add them up. We then don't know how much is steel and how much is concrete, we just know that total. So we could use a placeholder to tell us how we could transform one material into the other, or N. So we want to know our transformed area of, say, steel. Well, N would be the stiffness of the steel divided by the stiffness of the concrete. And we could use that to find our transformed area. Again, the best way to look at this is to do an example. So we'll do two examples now on this. So let's take that example we did previously with the HSS filled with concrete and transform the steel into concrete. We saw what stiffness would go where. We know that the combined total stiffness of this system must remain the same. And so then if we say we know what the stiffness of EA is, and we want to pretend that the EA of steel, that the E is actually this E, what corresponding area of steel would we need to make this system be the same? And that's all we're essentially doing, is pretending that the steel is actually concrete so that we can make some of our calculations a little bit easier. Again, it forgets about buckling and it doesn't talk about buckling, but this is a concept I'm trying to show you for a few other things. Let me make this bigger. So we're going to be using the same section. We've got our HSS 152 by 152 by 9.5 and our E of 30,000 MPa. We've already figured out E and A of steel, E and A of concrete, and we figured out the EA of steel and the EA of concrete. In fact, we figured out the total area and we figured out all of it. What we want to know is if we're transforming the steel into concrete, let's take a look at the area of the transformed section. So we're going to pretend that that EA of steel has an E of 30,000 MPa, essentially. So we want to change the ratio here to figure out what area we would need instead. So we had an area of 5,210 millimeters squared of steel, but we want to pretend that it is concrete. We had an E of 200,000, but we want to pretend it's only 30,000. So what area do we need instead then? So we have 5,210 times 200,000 divided by 30,000. We would need an area of steel of 34,733 millimeters squared. So if we pretended that the E of our steel was only 30,000 MPa, and we need the total EA of our entire system to stay the same, we would need an area of 34,733 millimeters squared of concrete to replace the 5,210 millimeters squared of steel. Or essentially, if this was all an E of 30,000 MPa, and this had our area of 17,689, and this is an area of 34,733, it is, and this is all concrete, this is equal to this. Essentially, we're saying we have a total area of 34,733 plus 17,689, or 34,733 plus 17,689, or 52,422 millimeters squared. So this system here has the same stiffness as this system here, all as concrete. So these two things would be equivalent from a strength and stiffness point of view, except for the fact that we have a buckling problem. We're not going to talk about buckling, we're not going to look at buckling, but it is a thing to bear in mind. But this can be a handy trick to kind of make some other things easier for us later on. Let's take a look at another transformed section example here for a second. If we have a 250 by 350 concrete column with an E of 25,000 MPa and 820 M bars. Now, you don't know much about rebar yet. We're going to talk about that next week, but I'll show you what that means area-wise. I'm going to draw my, remember here, there's just a note I want to write myself to check something for your assignment. Hold on a second, guys. I'm going to pause this and come right back. I just want to check if I'm consistent in something for you guys. Okay, so let's try that again. They've given us a concrete column. Oh, my pens are getting... All right. We have a concrete column that they've given us, they've told us is 250 by 350. And they have told us that the E of concrete is 25,000 MPa. So 250 by 350. And they've told us that there are 8 20M bars in here. We don't know the layout. This seems like something reasonable. We don't know much about reinforcement yet. So I'm going to give you what the area of a 20M bar is. An area of a 20M bar is 300 millimeters squared. So a single 20M bar is 300 millimeters squared, and we have 8 of them. And they've asked us to transform this section. Typically that means transform the steel into concrete. That's the norm. We're going to do both. We're also going to transform the concrete into steel, just for fun, to show you that it can happen either way. But typically what we do is transform the steel into concrete. So let's figure out what our E and A is of all of our bits here. So the area of the steel, we have 8 bars that are 300 millimeters squared each, or 2,400 millimeters squared. E of steel is the same. We know E of steel is 200,000 MPa. Area of the concrete. Now, when we were doing the HSS filled example, we removed the area of the steel because there was comparatively quite a lot of steel. You can do that. You can be thorough and do that. But typically, the area of the steel is so nominal compared to the overall area of the object that we don't bother. Now, I know you're sitting there thinking, what the hell are you talking about, Shannon? You just made us calculate the area, and it's all about the ratios. But when we're talking about the area of the concrete with the stiffness of the concrete, removing that tiny little bit makes almost no difference. When we're talking about the area of the steel, that little bit is the entirety of the area. So it has a much more significant value when we're talking about the steel itself. So for the area of the concrete, we're not going to remove the area of the steel. And I'll show you why. So we have 250 by 350 equals 250 by 350 equals 87,500 millimeters squared. Now, yes, if you wanted to be thorough, you could remove that area, but it's not how we're going to do it because industry doesn't do it that way. And here's why. If we had, let's just see what that ratio is. It's like removing about 2.5% of the concrete area. For the steel, 2,400 is 100% of its equivalent area or its importance of area. For the concrete, it's only 3% of its area, or somewhere less than 3%. So that 2,400 is much more significant to the steel than it is to the concrete. So we are not following industry standard, going to remove the area of the steel from the area of the concrete when we're talking about rebar. You could, there's nothing wrong with it. In fact, we did it when we had a larger object of steel combined with our concrete. But industry standard does it this way, so we're going to stick with industry standard. They gave us the E for concrete as 25,000 MPa. So remember, transforming the section is just saying if we had our total AS-ES, we want to just pretend that we want to find the ratio of ES. We want to make that, if we had the total AS and ES of steel, we want to see what the area would be if the E was actually 25,000 MPa. And that's what we do here. Let's do it both ways. Let's transform steel to concrete. This is typically what we do. We're also going to transform concrete to steel just to show you that it can be done. But normally what we're doing is this activity right here, where the transformed section is the area of the steel times the ratio of the E of steel to the E of the concrete, or 2,400 times 200,000 MPa divided by 25,000 MPa. 2,400 times 200,000 divided by 25,000 gives us 19,200 millimeters squared. So if we wanted to pretend our steel had an E that matched concrete, we would need 19,200 millimeters squared of it. So that would give us an effective area of our area of our concrete plus the area of our transformed section, or our 87,500 plus our 19,200, 87,500 plus 19,200, or 106,700 millimeters squared. So instead, we're saying, instead of a 250 by 350 concrete column with 820M bars in it, it is the equivalent of a concrete column with an area of 106,700 millimeters squared and an E of 25,000 MPa. So these two things are equal. We could figure out a square area of it if we wanted. Actually, let's do that. Let's take the square root of that just for fun. So it's similar to a square column that is 327 by 327. What if we kept one side the same? So 106,700 divided by 350. So instead, 350, instead of having a 350 by 250 concrete column with 820M bars in it, it's the same as a 350 by 305 concrete column with no steel in it, when we're talking about certain aspects of the design. Let's just for fun transform the concrete to steel. Not typical. This is not what we would normally do, but I just want to show you that this concept can work either way. So the area of the transformed section is going to be the area of our concrete times the E of our concrete divided by the E of our steel, or 87,500 times the E of our concrete, which was 25,000, divided by 200,000 MPa, or 87,500 times 25,000 divided by 200,000, and we get 10,938 millimeters squared. So our area effective would be our area of our steel plus the area of our transformed section, so 2,400 plus 10,938, or 13,338 millimeters squared. Let's just see. So about the same as a piece of steel that was 115 by 115. So we can transform either material into the other. We could have multiple materials in this if we wanted, and figure these things out. Remember, it's all about the total EA that we're talking about for these things. So now we have the ability to transform one material into the other, or allow us to talk about two materials as if it was pretending to just be one material. So now we can talk about the fun part. So we're going to talk about composite systems now. So if two objects or materials are combined so that they support loads as one, the system is said to be composite. In order for a system to be considered composite, the materials must be bonded so that they won't slip relative to each other. So what do I mean by slip relative to each other? If you take a stack of paper and you bend it, you can feel where your hands are at the edge that the top layers of paper kick out from the bottom layers. You can actually see that they're not in line with each other in a way that they were when it started. If you're doing it in your own hands, you can actually feel that slip happening against your hand. We're saying we're making it so that can't happen. That means that those pieces of paper would be glued together, for example. In axial loading, it's pretty easy. You just have to make sure they move together. In bending, it gets a little bit harder. We need to make sure that the shear can be transferred across the plane where the materials interface. They can be two different materials, or they can be two pieces of the same material, like wood, for example. Glulam beams are a really good example. So concrete has steel and concrete. Glulam is wood and wood. There are, I'm going to show you a whole range of composite materials at the end of the lecture. So composite versus non-composite, which means sharing the load. For bending elements, longitudinal shear is critical. If there's no bond along the interface or the shear plane, the elements will slip along that plane. Then it's just like you've got two small beams sharing the load. So if I take this stack of paper again, what's happening is these papers are all slipping along the planes relative to each other, or along the longitudinal shear planes. And so we've got, I don't know, if I have 50 pieces of paper here, I've got 49 longitudinal shear planes. What we're saying is that we don't let those slip relative to each other. If they do slip relative to each other, I've got 50 sheets of paper, which is better than one sheet of paper, for sure. 50 sheets is better than one sheet. But 50 sheets glued together is one piece of paper 50 times as thick as one sheet of paper. And you're thinking, that's the same thing, Shannon. but it is not. And we're going to show that in math in just a second. So we're actually going to do the calculation in a minute of two 140 by 140 timber beams spanning the same distance as a bending element. If it is non-composite or sharing the load, you can see that it slips along this plane, and we have two beams sharing the load. Two 140 by 140 beams, definitely better than one 140 by 140 beam. It's twice as strong. But if we glue them together, it's more than twice as strong. And we're going to show that it has more than twice as much capacity. You can see that we've prevented this line from slipping here. Here we have two stress profiles where we're going to hit our maximum stress that we can see at the extreme fibers pretty quickly. Here we have a further distance to get to our maximum stress profile that we can have based on the maximum capacity of that wood material. So non-composite, composite. So let's take a look at two 140 by 140 beams of the same material stacked on top of each other. We're going to calculate the shape properties for axial and shear, bending moment, and stiffness. Remember, both axial and shear are just area. Bending moment, the shape property is S, and stiffness, the shape property is I. And we're going to calculate it based on if it's composite and non-composite for both versions. Okay, so we have two 140 by 140 beams stacked on top of each other, and we want to calculate the shape properties for axial load and shear, which is area, bending moment, which is S, and stiffness, which is I, for both composite and non-composite versions. So let's take a look at what that means to us. Let's draw out what we've got here. So let's draw out our non-composite. So our non-composite, we have a (140 by 140 sitting on top of a 140 by 140. These are two separate objects that have not been bonded together. Composite means we have glued them together or attached them along this plane in a way that they work as one member. So we've glued in here in some way that we have one member that is 280 millimeters deep by 140. Let's calculate area. Well, area is B times D, or 140 by 140 plus 140 by 140. We've got area of that plus the area of that, or 140 times 140 times 2. We have an area equals 39,200 millimeters squared. For composite, we have 140 by 280, or area for composite equals 140 by 280. 39,200 millimeters squared. They're the exact same. You're thinking, Shannon, why are you wasting our time? These two numbers are the same. Why would we bother to make something composite? Well, area is the shape property we use for axial loads and shear loads. Let's take a look at the shape property we use for bending, which is S. Do you guys remember the formula for the shape property for S of a rectangle? It's BD squared divided by 6. So for our non-composite section, we have BD squared divided by 6 of the top member and BD squared divided by 6 of the bottom member, or 2 times B, which is 140, times D, which is 140 squared, divided by 6. So BD squared divided by 6, and we've got it twice. The section modulus for the non-composite version of this is 2 times 140 times 140 squared divided by 6. Or 0.915 times 10 to the 6 millimeters cubed. For our composite section, we have a B of 140, but a depth of 280, because this has been glued or bonded together in a way that this is one object now. So we have 140 by 280 squared divided by 6. So the section modulus for the composite version is 140 by 280 squared divided by 6. Ooh, we have 1.83 times 10 to the 6 millimeters squared. So this is bending. I'm recording. Did you find a mistake in something?
Yeah.
That's the worst. So for our area, the area of non-composite equaled the area of composite. For section modulus, the area of non-composite versus the area of composite just want to write this the right way. We have the area of composite is 2 times the area of non-composite. So making it, or it was 2 times the section modulus, sorry. So by making it composite, we have doubled the section modulus versus just sitting them on top of each other. So we have the same amount of material in both of these. The difference is that we've bonded it together. Not bonding it, it's better than one. One of them, the section modulus, would have been half of this. But by bonding it together, we actually have increased the section modulus. Let's talk about I, or stiffness. If you guys remember, it's BD cubed divided by 12 for a rectangle. B is 140, D is 140, and we've got 2 of them. Or 2 times 140 times 140 cubed divided by 12. The I for non-composite is 2 times 140 times 140 cubed divided by 12. 1, 2, 3, 1, 2, 3, or 64 times 10 to the 6 millimeters to the 4th. And for our composite section, we have a B of 140 and a depth of 280. So we have 140 times 280 cubed divided by 12, where the moment of inertia for the composite version is 140 by 280 cubed divided by 12. 1, 2, 3, or 256.1 times 10 to the 6 millimeters to the 4th. So this is stiffness, or bending stiffness. I composite is 4 times the I of non-composite. So by making this composite along this line right here, using the same amount of material, the only thing we've done between these two things is make sure that's bonded together in some way, we get twice the strength and 4 times the stiffness. So by making things in bending composite, we get a huge advantage. It doesn't give us much advantage for axial loads or shear, which are dependent on area, except, like Dave pointed out, if we have a buckling problem. So if we had this restrained in this direction and we were only worried about buckling in this direction, both of these would buckle easier than this one in this direction, because they each only have an effective depth of 140, whereas this has an effective depth of 280. But we're not focusing on that. The big takeaway I want you to see here is that making it composite for bending helps us with strength and it helps us with stiffness. It has a huge impact on our design. So by making something composite, we're effectively making it deeper, which we learned previously had a really big impact on our design techniques. So composite, if we can do it in a relatively easy way, can be really advantageous for us. But it has to have this bond along that plane to make it composite. So again, you can see that worked out right here. So that's really the hard part of the lecture. There's not a lot of math to it. We looked at load sharing for columns and how the load goes to the stiffest path, and that can be dependent on the material stiffness and the amount of the material. We looked at transforming the section, and we looked at the relative merits of load sharing in bending versus composite action in bending. And so we could see that we got a real advantage for bending materials. In axial loaded elements, it really didn't make a difference whether it was load sharing or composite. We got no advantage out of making it composite. There wasn't really much it added to it. Didn't hurt if we made it composite, but sometimes in certain situations it can take a lot of work or a lot of effort to make them composite. So for axial loaded elements like columns, it's not necessary to make it composite because it's going to do the same job whether it's composite or not. It's going to share the load.
Unless it's slender and you have to worry about buckling.
Oh.
That's a bending stiffness phenomenon.
That is a solid point, John David Bowick. If you had a column and you were worried about buckling and you had two separate materials, they would each want to buckle easily. Now, I know I said we're not going to talk about composite action in combination with buckling, but if we made it composite, we have a better stiffness of the overall system. Remember that E value change, or our I increases more drastically by making it composite, which means we can get a better buckling result. So that's way beyond what we're talking about in this class, but we got the peanut gallery over here lobbing balls at me, trying to hit them out of the park. It could help with a column if we were worried about buckling. But mostly, we really take advantage of composite action for bending elements. That's where we really see a huge advantage in composite systems. So what are some composite systems? We've talked about glulam, and we've talked about steel in concrete. But here are some other ones. When we had our concrete on metal deck, remember I talked about last term these little holes that got punched in the side to make the steel and the concrete work together? Well, that was our longitudinal shear plane. That was making sure that the concrete and the steel don't just slip past each other. Otherwise, we'd have a small thin deck and a somewhat thin concrete deck working together, which is great. But by binding them together, we have our steel doing all the tensile work at the bottom, and the concrete doing all of the compressive work at the top, instead of steel doing a little bit of tension and a little bit of compression, and the concrete doing a little bit of tension and a little bit of compression, which we know steel is really good in tension and concrete is really great in compression. Making them composite makes them each do their best job and focus on that. We can make a steel beam composite with composite decks if we want. These shear studs, or Nelson studs is sometimes what they'll be called, get shot through the deck into the steel beam, so it bonds the deck and the steel, and then they cast the concrete around these steel studs. So what we end up with is those are a section mark saying I've stopped drawing. Instead of just a steel beam with deck applying load, we end up with a steel beam that looks like this with concrete up here at the top doing a big chunk of the compression job. Now, this doesn't help with vibration, and a lot of the times in our market, we're worried about vibration anyway, and so we don't get a huge amount of advantage out of doing this. There are applications where you can design these shear studs and they would have a big impact in reducing the material use in your system. But most of the projects I work on, and a lot of the ones in Toronto, the steel needs to work for vibration as well, and so doing this system doesn't add a lot, but you definitely see it out in the market. Do you remember that system factor we were talking about with wood when we had our plywood on our joists or plywood on our studs? What we're saying is that we're actually making use of some of this plywood here. We're effectively, remember all of those clauses depended on how well these were either glued or nailed together? Well, that is our longitudinal shear transfer plane right there. If these are nailed or screwed together really well, which they often would be in a house, we get a little bit of benefit of making use of that plywood. Wood eye joists. There's a lot going on there. The board that is the web, it itself is composite. It's a bunch of pieces of wood glued together, so it's composite. But then it's acting compositely with the top and bottom flanges. We have to glue it in there to make sure they don't slip relative to each other, and that's what makes it act as one big system. Sit panels, where we've got plywood glued to styrofoam or foam of some sort glued to another piece of plywood. Instead of just having two pieces of plywood, we have a top and bottom chord of one deep beam. Flitch beams. Now this one's interesting because look at them. We actually don't have that much of an issue here. These are more working as load-sharing elements. The fact that we make them composite is to force them to move together. So we make sure they're screwed together so that they move together. Where we use flitch beams, it's not an easy, it's an expensive system. We certainly don't start with flitch beams, which is we've got wood and steel plates in combination. Where we would make use of them, for example, is if our beam just didn't work or it was too big to maybe fit in our wall system. By using the steel plates, which are smaller than the equivalent wood area that we need, maybe now we can fit this in our wall system. So there's a few different ways we'd use flitch beams, but it's not where we'd start. We've talked about glue lam. These are a series of 2x material on top of each other. And rather than just have 1, 2, 3, 4, 5 2x6s on top of each other, which is definitely better than 1 2x6, if we glue them together, we have one beam that is this deep. And we've seen the impact on that on our section modulus and our moment of inertia, which is strength and stiffness, by making it composite. These are just other glulam applications here. CLT, again, we take a series of boards in this direction and then glue on a series of boards in this direction and then glue on a series of pieces of wood in that direction. Again, that glue joint in between them. Many plants don't even glue the pieces of wood butting up against each other. They only glue in between the planes of the lumber. And you can have advanced composite systems as well. So this would be something like a Kevlar fiber or carbon fiber, which is very, 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 very strong. But it's super duper thin, and it is not very stiff in compression. So you can see that we wouldn't want to make a Kevlar column, and it's very, very expensive. So where it adds a lot of benefit is in rehabilitation for concrete, for example. So the under the gardener, where the concrete in tension at the bottom is spalling and exposing the steel, so the steel is rusting, they can come in and glue on sheets of Kevlar to do that tension job. So the concrete at the top is still doing a good job in compression, but now we might have this Kevlar strip at the bottom doing the work in tension. Again, we would not start with that as a design because it is very expensive, but if we're trying to rehabilitate something or extend the life rather than build a whole new building, tear one down and build a new one, the cost of this starts to maybe be quite reasonable. So we're going to take a breather now before next week we jump into concrete design. And then that's the last of the new design material we're going to introduce in our structures curriculum. So we're almost done. We're almost at the end. Today we learned that the load follows the stiffest path, and that stiffness can be based on the stiffness of the material and the amount of the material we have. Load sharing is additive. Composite action makes a member act like it's a bigger member. Longitudinal shear is required for composite action in bending. We need to know how to calculate load sharing in a column. We should know how to calculate the transformed section. And we should be able to tell the difference between load sharing and composite action. Where are the advantages and what does it get us? So next week, concrete.